In this lecture, I would like to focus on linear data structures. Stacks, queues, and dequeues behave like a list, but they differ in the order of adding new items and the positions where items can be accessed and removed from the list. The design to allow the access of an item from one end but not the other seems restrictive, but it actually makes it easier and sometimes more efficient as well to translate a real-world problem into a computer solution. So here is a stack of books. When you put one on top of the other, there is a natural order in which the books are placed in a stack. You start with the one in the bottom and add another on top, and continue that way. When you remove it, the most natural way I would suggest is to remove one book at a time from the top. So regardless of whether you are to add or to remove, you access the stack from the top. Because of this mechanism of placing one on top of the last and pushing it down, a stack can be thought of as a push-down stack. It is an ordered collection of items where the addition and removal happens at the same end, that is, the top. Think about this. When you try to remove a book from a stack, you first remove the last item you put in. So a stack is in fact last in, first out. Imagine you are to design a stack data structure. Perhaps here are some of the operations or methods you need to have: to push or to add a new item to the top, to pop or to remove the last item, and to check the size of the stack, that is, the number of items in it. If you run this particular piece of code, the implementation of a stack here, it will work fine, but you get nothing from it. For now, this only defines the class or the blueprint of what a stack is. Until you construct an actual stack instance based on the blueprint, it is not real yet. Let's look at the stack blueprint or class first. The init function is the constructor function that will be called when a new stack instance is created. And at the very moment of creation, whatever code you have here will be used for initialization. Here, self refers to the new instance just created, within which you have an items variable holding an empty list with the square brackets. The other functions implement related methods we discussed earlier to add, to remove, and to access the last top item in the stack, as well as those to evaluate the size of the stack. Now that we have the class or the blueprint, let's create some stack instances based on the blueprint and put them into action. So in the code, we have first create an empty stack cards by calling the stack constructor, which executes whatever you have in the init function. Next, we push or add new cards to the cards stack. And when we take a look with the peek function, we can only access the last one, which is the king on the top. And now if we call the pop function, we will remove the king, which is again on the top. So I just show you an example of a stack. But people may ask, why do we need stacks? Isn't a list more flexible than a stack? Because what it takes to implement a stack class just now was basically a list. Why do we need first in, last out, or last in, first out? Isn't that restrictive and making programming more difficult? These are very natural questions from students, but there are applications where the restrictive design is a blessing. When the problem you try to solve also exhibits the same restrictive characteristics, the design will make sure related assumptions and conditions are not violated. In fact, the proper mapping of the problem space and the design makes coding much easier. Let's take a look at a real-world problem. Imagine you write a math formula. So whenever you open with the open parenthesis, you will have to close it properly with the closed one. The whole equation should be balanced. That is, if you have two openings, you will have to have two closed ones as well. So the first equation here looks good. Everything is balanced. But the second equation here is incorrect because you have extra closed parentheses, which make the equation invalid. So let's try to create a piece of code to check the balance of a math equation using the idea of a stack. Now this code may look confusing at the beginning, so let's go through the steps. So for now, we hard code the math equation or formula to show the basic idea. You can certainly make this a function or even a method of a class so you can reuse it later. We create an empty stack called S first and assume the result to be correct with the balanced variable set to be true initially. Now we set this to be true until we find something wrong in the process. Now we take each symbol in the equation m from left to right, which is what the loop does. And for each symbol, we look at what the symbol is. Okay, if it's an open parenthesis, we push it to the stack. If it closes it, if it's a closed parenthesis, there are a couple of conditions we need to look at. So if it's a closed one and the stack is empty, that means there has no open parenthesis before this closed one. That means the whole thing is not balanced. And so in this case, it's problematic, and we are going to set balanced equal to false. Now the second condition is that if the stack is not empty, that means there has already been a parenthesis or two already in the stack. Now with the closed one, they are balanced out, and we should remove or pop the last open parenthesis. Okay, so in this case, it's still balanced and everything is good. We don't need to do anything about the balanced variable. Let's go through the process of the loop to see how this works. There are 15 steps here because we have 15 symbols in the formula. Now in this math checker, what we really care about is the opening and the closing parentheses. Okay, we care about nothing else. So the first step, we are going to encounter 7. We'll skip, minus, skip. The third step, when we see the open parentheses, we are going to add it to the queue. So there is one open in the queue. and the balanced remains true. Okay. For step 5, we are going to skip, and we skip plus. In step 6, we see another open parenthesis. So we add this to the queue as well. So there are 2 open parentheses in the stack. Then 2, skip, plus skip 3. In step 10, we see a close parenthesis. Now when we see a parenthesis, according to the code earlier, we're going to check whether the stack is empty or not. Now that the stack before this step 10 is not empty, we're going to pop the last item, which is one of the open parentheses. Okay, so after the popping, there is one open parenthesis remaining in the stack. Okay, so we still have one that is not balanced out yet. And we'll continue the process until we reach step 15, when we have another close parenthesis to balance the existing open one. Okay, so the whole thing will become empty and the balance will stay true. Okay, so this is a valid formula with the same number of open parentheses and the close parentheses. Now let's take a look at one that is not balanced. Remember the second example that we had earlier with the extra close parentheses. Okay, so this is just adding 2 extra close parentheses to the earlier formula, which was correct. And so it's going to follow the same 15 steps that we discussed earlier. Okay, so the process will continue with a few more steps with the extra parentheses, close ones. Now that the stack is already empty at step 15, and now we encounter another close parenthesis, it's going to trigger the if condition. And the if condition says if the stack is empty, then we are going to set balance to false, because what you're encountering here is that you have a close parenthesis, but there is no open ones, and so this whole thing is not balanced. And with this check equation code, it's going to say this whole formula is not balanced. Okay, so it's not valid in the end. Now let's look at another example where instead of having extra close parentheses, we have extra open parentheses earlier in the formula. So with the extra opening parentheses in the formula, they will be added to the stack early on. So in the end, there are not enough close parentheses to balance them out. So after the loop, 2 open parentheses will remain in the stack. So even though at the end the balanced variable remains true, because of the if condition here, the stack is not empty, the balance variable will still be set to false. Let's talk about queue. I suppose you don't like waiting, especially if you are late and there is already a long line. It might be tempting to push in, but you are not supposed to do that. A waiting line is a queue, and the rule is first come, first served. A queue is defined as an ordered collection of items where the addition of new items and the removal of existing items occur at the different ends. This is quite the opposite of a stack, where you access from the same end. So queues are first in, first out, or first come, first served. Again, imagine you are designing a data structure to solve a problem related to queues. Here are potential operations you need to include to support the construction of related algorithms. For example, enqueue to add a new item to the end, dequeue to remove one from the front, and methods to check the size of the queue. So the queue class is similar to the stack class we implemented earlier, both using a list to store items. The dequeue method is similar to the pop in the stack class, which removes an item at the end of the list. Here, conceptually, the end of the items list is in fact the front of the queue. Conversely, the enqueue method adds an item to position 0, which is, in this case, the rear of the queue. So the two methods are accessing items from different ends of the queue. Queue has a wide range of applications, from business transactions to printer jobs to any processes where things get done on the first come, first served basis. The example here shows a sequence of actions to place orders or to add orders, to get them processed and served, or to get removed. Dequeue is an extension of the queue structure. Dequeue, or a double-ended queue, is an ordered collection of items with two ends, the front and the rear, and items can be added and removed from both ends. In this design, a dequeue has all capabilities of a stack as well as those of a queue. It is no longer last in, first out, or first in, first out. If dequeue sounds like a weird idea, think about a train. You can add or remove cars to the end of a train. Likewise, you can attach them to the front. An engine can be attached to either side depending on which direction you want to go. When designing a dequeue type, you need to have methods to add and remove from both ends. Here you see we have the add front, add rear, remove front, and remove rear. So they allow access from both ends to remove or to add. Compare this dequeue class code to the queue and the stack that we had earlier. It is in fact a combination of methods from the earlier two classes, in different names though. Imagine you are to arrange a train engine with different cars. You can play with the code here to see the different orders in which the same sequence of cars can be constructed.